these band gap come from. So here we're trying to explain the origin of the band gap, and we were trying to do this from two perspectives. First, using the physics way, which is looking at square well or particle in a box type problem, and then extrapolate to multiple box, which each box, of course, can be thought of as one of your atoms in your lattice in a periodic functions. And then later on, we're going to talk about it from the chemistry point of view, which is using molecular orbital theory. So again, both of these can give rise to energy band structure. So I think hopefully people has a feel for this, even though the map appears from time to time maybe a little bit involved. But I think we don't expect you to be able to derive it, but we should. But you should see some of the features, the key features that come out from this sort of mathematics that lead to these band structure. Okay, so just very quickly again from before we were looking at these particle in a box solution. So the particle in a box solution is quite simple. At least if you have done, some of you may have taken quantum mechanics course, you would realize this. That particle in a box, you solve in quantum mechanics, you solve a what they call a differential equation, which is in the form of like this. Okay, so this is a typical differential equations called Schrödinger equation, which have a Hamiltonian part and the total energy part. And you solve this by trying, in most differential equations, the way to solve the problem is try and error. So if you try a trial function like this, which consists of a linear combination, so if you have A and B are just coefficients that combine these two functions. This function is e to the ik dot I. That's what we call a plane wave. Moving in the x direction, and this is moving in the negative x direction, and the directional vector, the propagation vector, what we call propagation vector, is the k direction. So that's the sort of the k vector pointing the wave vector pointing in x and pointing minus x. So the picture you have is this kind of wave, traveling wave, plane wave, going in two directions, and of course, by playing around with this A and B coefficient, you can tune to any wave that you want. You can adjust to anything that you want. So if you plug this solution into this differential equation, you solve this problem, you get some constant. This is called eigenfunction equation. So you have you basically operate on this function. You get a constant times the function itself. So this is why it's a special class of equation in mathematics called the eigenfunction equation. It's special because you do some operation and then you get some constant out times the function itself. So that's why it's a function. And this is eigenfunctions corresponding to the characteristic function, so-called characteristic function or characteristic value along with this function that you got. And this eigenvalue corresponds to the energy when you do this. And the energy, of course, will be just some constant proportional to k squared. K squared is, of course, the wave vector that we've been talking about. And so it's quite similar to classical mechanics. The energy is p squared divided by 2m. And p is the momentum. Momentum is, in this context, is some constant times the wave vectors. Okay. So this is quite easy to understand, and you only have kinetic energy. So this energy corresponds to kinetic energy. There's no potential energy here because you have free electrons. Okay. So then you got this, from here you can then extrapolate from the free electron, put this electron in a box, right, in a potential well. So this potential well is like this, a one-dimensional potential well, where the wall is infinite, so you have hard wall, you trap the electron inside this well. The electron cannot escape. What that means is that the wave function outside, the probability of finding the electron outside is 0, so therefore everything is trapped inside this infinite, sometimes infinitely high square well like this. So here you're starting to introduce, so here we have, in the free electron model, you don't use any potential energy in the square well problem. You approximate something very simple for this potential. And this potential has several regions. There's 3 regions to it. There are 2 regions corresponding to outside the well, and 1 region corresponding to inside the well. So this is inside the well. You set this potential to some constant, and 0 seems to be an easy way. You set the potential to 0 inside the well, and outside the well is infinite, so everything is trapped. Okay, and again you solve for this equation, and so you solve for, in particular, the way you solve for this thing is that you solve this differential equation this way, okay? Plus the potential energy in 3 different regions, and so here you look at just the region inside the well. Again, you have something that look like the free electron case. Why? Because the potential here is set to 0, because we set it to 0. So it look exactly like the free electron case, except, of course, now so the form almost look exactly the same. You have some operating double differential on the wave function, sometimes equal to some constant times the wave function, and you put in some quantum number n here to indicate that this is a little bit different, and we'll see why it's different. The reason why it's different is because of the boundary condition, so-called boundary condition. In quantum mechanics, you require the wave function to be continuous. In other words, the function itself cannot have a break in space. Okay, so it must be continuous. It means that, so we say that the wave function value, right, outside the well must be 0 because it's trapped. You cannot find any chance of finding the wave function outside, so it must be 0. Inside the well, you should find your wave function. So at the boundary point, in other words, at the wall of this well, the function inside the well must be the same as the function outside the well, because that's where the boundary is, right? The 2 values must be the same in order to create a continuous function for the wave functions. Okay? Because of this boundary condition, right? So this is the boundary condition, whereby here I'm talking about the wave function inside the well. So the boundary condition are x equals 0 and x equals L. And both of these wave functions must equal to 0 because you have no wave function outside. And due to this effect, what you got is that your solution become sine functions, and you emerge this k number. This k number, unlike the free electron case where k can pick on any value, as you can see, k here can, in the free electron case, k can pick on any value. There's no constraint, there's no integer requirement in here, whereas in here, there's some integer requirement whereby n is the quantum number, and quantum number is the integer number, so that to create a quantized wave vector, okay? And furthermore, due to this quantization, your energy is also quantized, because your energy is proportional to k squared, and k is quantized, so therefore energy is quantized. So the effect of the boundary condition is severe